In this video, we're going to go over a little proposition of two statements, A and B, so make sure to look at the timestamps if you want to skip anything. So we have two functions, f and g, which are invertible. So this proposition only works if your given functions are invertible. Our statement A says that the inverse of f is going to be invertible, and the inverse of f is f itself. And B, what we're saying is that G circle F is invertible, and its inverse is F inverse composed with G inverse. All right, let's start with A. By definition, F composed with F inverse will give you the identity over B. And when you take F inverse composed with F, it gives you the identity over A. Now, to say that F is invertible means that we have a function such that when you compose it with f, it gives you the identity function. And it's the same thing for f inverse. We want a function such that composed with f inverse, it gives us the identity function. But this is exactly the role that f plays in this composition. So we've proved that f inverse is invertible, and its inverse is actually f. So when you take f, the inverse of f inverse, it gives you back f. And that's it. For the part B, we're going to have two functions again. Oh, that is a thick pen. We have two functions, f and g, which again are invertible. And we want to show that their composition, g circle f, is invertible as well. Now, the way we're going to go about this is showing directly what is the inverse of g circle f. In fact, it's the inverse of f circle the inverse of g. So you take the inverses of the two functions f and g and you compose them in the opposite order. Now, more specifically, what we're going to do is take g circle f and consider this as one function, and we're going to take what we claim to be the inverse of g circle f, so the inverse of f circle the inverse of g, and show that this is equal to the identity over c. And then we're going to do this in the opposite order. We take what we claim to be the inverse, compose it with g circle f, and this should be equal to the identity over A. Now, I encourage you to at least pause the video to make sure that you understand why it's the identity over C and the identity over A. Now, let's actually verify the first equality right here. So we take g circle f, circle f inverse, circle g inverse. That's a lot of circles, my goodness. Now, what we're going to do here, this is the only thing that we're going to do, is use the fact that the composition of functions is associative. So we can move around the parentheses however we'd want to, and it's not going to change anything. So we take g circle f and prioritize f circle f inverse. So circle g inverse. And now what this is equal to is the identity over b. Let me bring that down a little bit. We have the identity over b here, circle g inverse, and right in front we have circle g. Now, the identity over b really is useless. We can just simplify this as g circle the inverse of g. And what this is, it's simply the identity over c. Now again, we're going to do the same thing in the opposite order. We take what we claim to be the inverse, compose it with our g circle f. Now this is equal to, again, we're using the fact that composition is associative. So we're prioritizing the inverse of g, circle g. And what this is equal to, it's the identity over b again. Circle f, circle the inverse of f. Once again, the identity over b is useless. We can just simplify this as the inverse of f, circle f, and this will give us the identity over A. So in one proof, we've shown two things. That g circle f is invertible. It satisfies the definition of an invertible function. And we've also shown that its inverse is f inverse circle g inverse.